In this video, we're going to take a look at how to find Taylor polynomials and Taylor series for a given function. Recall that for any function f of x, the Taylor series of the function at x equal a is the power series from n equals 0 to infinity of the nth derivative of f evaluated at a divided by n factorial multiplied by x minus a to the nth power. If the Taylor series is constructed at x equal to 0, we call that Taylor series the Maclaurin series, and that's given by the power series from n equals 0 to infinity of the nth derivative of our function f evaluated at 0 divided by n factorial times x to the n. The Taylor series and Maclaurin series of a function are both important because if f of x is going to have a power series representation centered at some value x equal to a, then it turns out that the Taylor series at x equal a must be that power series representation. If we want a power series representation centered at 0, that would be the Maclaurin series of our function. So in either case, the c sub n, the coefficient in the power series representation for our function, is given by the nth derivative of f evaluated at our centering value a divided by n factorial. As with any series, a Taylor series or a Maclaurin series of a function can be approximated by their partial sums. If we have a Taylor series for a function, we call the partial sums of that Taylor series the Taylor polynomials of our function. Here we have formulas for the first four Taylor polynomials, p sub 0, p sub 1, p sub 2, and p sub 3, where p sub k denotes the kth Taylor polynomial for our Taylor series. Notice that the formula for the kth Taylor polynomial is just all of the terms of our Taylor series starting at n equals 0 and going to n equal to k. So p sub 0 is just the term of our Taylor series corresponding to n equals 0, which is f of a. P sub 1 is the Taylor series from n equals 0 to n equal 1, so f of a plus f prime of a times x minus a, and so on. Each Taylor polynomial has one additional term added onto it from the previous one, and we could, of course, continue on in a natural way to define p sub 4, p sub 5, p sub 6, and so on. If we start with the Maclaurin series for a function and want to find the partial sums of that series, these polynomials are called the Maclaurin polynomials and are given by the exact same formulas as the Taylor polynomials, except a is going to equal 0 throughout on the right-hand side of each polynomial. In this example, we want to find the third Taylor polynomial, p sub 3 of x, for the function f of x equals natural log of x at x equal to 1. Since we're looking for p sub 3, or the third Taylor polynomial, we need to find the values of the first four coefficients in the Taylor series for our function, which are c0, c1, c2, and c3, where we have c sub n being given by the nth derivative of our function evaluated at 1, since we want the polynomials about x equal to 1, divided by n factorial. We can find these values systematically by first finding the various derivatives of our function that we need. So here we're going to start with f of x being the natural log of x. And in order to get up to c3, we need to find the first three derivatives of this function. So we know f prime of x will be the derivative of natural log x, which will be 1 over x. Or, if we prefer, we could write that as x to the negative 1. The second derivative of f will be the derivative of 1 over x, or x to the negative 1, which will be negative 1 over x squared. Or again, we could write this as negative x to the negative 2. And our third derivative will be the derivative of our second derivative, which will end up being positive 2 over x cubed. Since we want the third Taylor polynomial here, we can actually stop differentiating once we reach the third derivative of our function, which is what we have here. Now that we have all the derivatives that we need, we can evaluate all of these at x equal to 1. So f of 1 is going to be the natural log of 1, which will be 0. F prime of 1 will be 1 over 1, which will be 1. F double prime of 1 will be negative 1 over 1 squared, which will be negative 1. And F triple prime of 1 will be 2 over 1 cubed, which is equal to 2. And so here are the numerators for all of our coefficients, C sub n, that we will need for our third Taylor polynomial. And now that we have these, we can find the coefficient C sub n by simply dividing each of these derivatives evaluated at 1 by the appropriate factorial. So C sub 0 will be f of 1, which is the 0th derivative of f evaluated at 1, which is 0, and we'll divide that by 0 factorial, which is 1. And so C sub 0 will be the constant 0. C sub 1 will be our value of f prime of 1, which is 1, divided by 1 factorial. So 1 divided by 1 will give us a 1. C sub 2 will be f double prime of 1, which is negative 1, divided by 2 factorial. So we have negative 1 divided by 2, which is negative 1/2. And last but not least, we have C3, which is f triple prime of 1, which is 2, divided by 3 factorial. So we have 2 divided by 6, or 1/3. Now that we have all of these coefficients, we're able to simply write down the third Taylor polynomial of the natural log of x at x equal to 1. We start with our C sub 0 term, which is just 0. And of course, since we're just adding 0 here, we could simply omit that, but we're going to include it here just for completeness and to make clear where we're using all of our quantities. The next term in our Taylor polynomial will be C1, which is 1, times x minus 1. We then add C2, which is negative 1/2, times x minus 1 quantity squared. And our last term will be plus C3, which is 1/3, times x minus 1 cubed. And if we want, we can clean this up just a little bit. The 0 does not need to be included, nor does the multiplying by 1 in the first term. But everything else is pretty much simplified to the best way possible, unless we're going to expand out everything. But here, our third degree Taylor polynomial P sub 3 will be x minus 1 minus 1/2 x minus 1 quantity squared plus 1/3 x minus 1 cubed. If you'd like to try a similar example, you can pause the video and find P sub 3 for the function f of x equals 1 over x squared at x equal 1. You can resume the video and see a full solution in a few seconds. To find P sub 3, we first find the function f of x, 1 over x squared, and its first 3 derivatives. Here, f prime of x will be negative 2 over x cubed, f double prime of x will be 6 over x to the 4th, and f triple prime of x will be negative 24 over x to the 5th. We then evaluate each of these functions at x equal 1, since that's the value for which we're finding the Taylor polynomial about. Here, f of 1 will equal 1, f prime of 1 will equal negative 2, f double prime of 1 will equal 6, and f triple prime of 1 will equal negative 24. We then find our coefficients by dividing the nth derivative of f at 1 by n factorial. So c sub 0 will be 1 divided by 0 factorial, which results in 1. C sub 1 will be negative 2 divided by 1 factorial, which gives us negative 2. C sub 2 will be 6 divided by 2 factorial, which will be 3. And C sub 3 will be negative 24 divided by 3 factorial, which will give us negative 4. And this means that our Taylor polynomial P sub 3 of x is given by 1 minus 2 times x minus 1, plus 3 times x minus 1 squared, minus 4 times x minus 1 cubed. Now that we have an algorithmic procedure to finding the Taylor polynomials for a particular function, we can use that exact same procedure to find the Taylor series of our function. In this example, we want to find the Taylor series of the function f of x equals natural log of x at x equal to 1. Note that earlier in this video, we found the third Taylor polynomial for this particular function at x equal 1, and we can reuse the derivative information that we found in that example. Here are the derivative functions, the derivatives evaluated at 1, and the coefficients for our Taylor series for n equals 0, 1, 2, and 3, namely the information that we needed to find the third Taylor polynomial. We could continue on in each of these columns for as many values as we want. For example, if we wanted to find the information for our n equal 4 term, we could find our fourth derivative of our function here by differentiating 2 over x cubed, which would give us negative 6 over x to the fourth, again using the power rule there. We could then evaluate that at 1 to get that f, the fourth derivative of f evaluated at 1 would be negative 6 over 1 to the fourth, or negative 6. And c sub 4 would be then that value, negative 6, divided by 4 factorial, so negative 6 over 24, which would be negative 1/4. At this point, we should be able to look at the values for c0 through c4 and come up with a formula for c sub n, the coefficient of the nth term of our Taylor series for our function f of x equals natural log of x. First, note that because of c sub 0 equaling 0, we're actually going to start our power series at n equal to 1. We could certainly start at n equals 0, but that first term, that 0th term, will be 0, and so it will add nothing to our Taylor series. And so for simplicity here, we're going to start our formula at n equal to 1. From there on out, we see that the coefficient c sub n is going to be a fraction, and the numerator is either going to be positive 1 or negative 1, depending on the index of n, the value of n. And so here we notice that when n is even, we get a negative 1, such as in c2 and c4. And when n is odd, we get a positive 1, and that happens when we have c1 and c3. So this gives us a possible formula for our numerator of negative 1 to the n plus 1. If n happens to be an odd number here, then our numerator is negative 1 raised to an even number, n plus 1, and therefore is positive 1. And if n is an even number, the numerator is negative 1 raised to the odd number, n plus 1, which is negative 1. And so this will give us our alternating sign in our numerator. In each of the denominators, notice that the denominator is just simply the subscript on the coefficient. So 1/3 is the value of c sub 3, negative 1/4 is the value of c sub 4, and negative 1 to the n plus 1 over n will be the value of c sub n. Now we have a formula that gives us all of our coefficients for our entire Taylor series. And so we can simply write down our Taylor series in standard series notation. Recall here that we're starting our series at n equal to 1, going through infinity, instead of n equal to 0, like in most power series. And again, that is just because c sub 0 is 0, so including it does not make any difference in this particular series. And so once we have this, we can substitute in our coefficient. We have negative 1 to the n plus 1 over n. And of course, we're going to have x minus 1 to the nth power. And so here is our Taylor series for natural log of x at x equal 1, given in compact sigma notation. If you'd like to try a similar example, you can pause the video and find the Maclaurin series for f of x equals 1 over 1 plus x. This looks a little bit different than the previous example. However, recall that the Maclaurin series is simply the Taylor series at x equals 0. And so you can do this problem exactly the same way as the previous example by finding the first several derivatives, evaluating them at 0 in this case instead of 1, and then using that value to find the coefficients. Once you have a list of coefficients, you should see a pattern, and from that you can derive a formula for the general coefficient c sub n, and then write down the Maclaurin series for the function. You can resume the video in a few seconds to see the full solution. We're given that f of x is equal to 1 over 1 plus x, and we find the first four derivatives of this function. F prime of x is negative 1 over 1 plus x quantity squared. F double prime of x is 2 over 1 plus x quantity cubed. F triple prime of x will be negative 6 over 1 plus x quantity to the fourth. And the fourth derivative of f is 24 over 1 plus x to the fifth. Each of these derivatives can be computed by rewriting the denominator with a negative exponent and then using the power rule. We then evaluate each of these functions at 0 because here we're looking for the Maclaurin series, which is the Taylor series at 0. When we evaluate each of these at 0, we obtain the values of 1, negative 1, 2, negative 6, and 24, respectively. We then divide each of these values by n factorial to get the values for c sub 0 through c sub 4. When we do that, we get c sub 0 equal to 1, c sub 1 equal to negative 1, c sub 2 equal to positive 1, c sub 3 equals the negative 1, and c sub 4 equal to positive 1. The obvious pattern here is that whenever we have an even index, so c sub some even number, we get a positive 1, and every odd indexed value is going to be negative 1. And so we can find a formula for c sub n, which is given by negative 1 to the nth power. We can then substitute that into our general form for a Maclaurin series, and we obtain the Maclaurin series n equals 0 to infinity of negative 1 to the n times x to the n.